Hello everyone, welcome. Today, Jack wants to talk about data structures. And we're going to be talking about how, again, data structures and algorithms are closely tied together. In fact, we're going to go back to our binary search algorithm from our algorithms chapter and look at that as a tree. So we'll be getting into that. We'll also talk about binary searches needing and assuming a particular capability of data structures, whereas linear searches do not assume that same capability. We'll talk about that. Again, data structures and algorithms are very, very closely related. And we'll talk some about arrays, and we'll talk very, very briefly about stacks and decks and queues, and we'll talk some about trees, again, in context of our binary tree. And we'll also talk a little bit about pointers. So let's start out with our binary search tree. And I have it right here. And this is from page 278. It was one of the examples in the book. And these numbers are the numbers of the entries in the binary search. Remember, in the binary search, this particular list, as it was given then, has 15 members, and I numbered them from 0 to 14. The midpoint of that would be 7. So to do a binary search, we have our list, we go to the midpoint, and then depending on the relationship of the midpoint and what we're searching for, we say, well, it's above or before this point, or it's below this point. And this particular example was looking for John. And John will come later than Harry, so we ignore everything to the left of here before Harry, and we just consider everything to the right. Well, now we start our algorithm again. Larry is a root of this subtree, just like Harry is the root of the whole tree. Larry is the root of this subtree, and we say, what is the relationship between John and Larry? John comes before Larry, so we will ignore this subtree, the ones after Larry, and we will come down here, and John is the root of this subtree, and it turns out John is what we're looking for. And that's what the example in the book went through, using a list or array kind of structure for all these elements. I put this up here to show that an ordered list of things can also be represented as an array, assuming that you can get to the items directly. And I also wanted to show you how the binary search algorithm is what we refer to as a recursive algorithm. We have our thing we're looking for, John in this case, and we go to the root of our tree and we say, are you John? The answer is no. The next question is John to the left or the right of you? In our case, John was to the right of Harry, and so we go down to this Larry node. We treat Larry as the root of its subtree, and we ask the same question. Are you John? No. Is John to the left or the right? To the left. So we go down here to the root and treat John as the root of this subtree, and we say, are you John? And in this case, the answer is yes. The other way, the other case that I did not talk about in this example is the subtree is empty. So if I had been looking for, let's see, Nathan here, and I would have said, is Nathan before or after Nancy? And the answer would have been after. So I would have gone down here and treated this as the root of this subtree. And I would have said, Nate, are you Nathan? The answer is no. Are you before or after Nathan? Or is Nathan before or after you? Before. Well, this subtree is empty. So if I hit a case where the subtree is where my tree is empty, subtree or no, the search has failed. What I'm looking for is not in the tree. So that's our recursive algorithm for binary searches. Is my tree empty? No. Is the root I'm looking at the same thing as I'm looking for? Yes, great. No. Do I go to the left or the right? Or is what I'm looking for to before this root, or after? And so that will let me traverse this tree in an orderly and recursive fashion. Now, notice that this binary search algorithm relies on our being able to pull up any element of the list directly. So it assumes that my list is ordered, and it assumes that I can get to any list at any point. And some of the data structures that we're going to be looking at in just a few minutes do not have that quality, and so they would not be applicable. And also, as I said, the binary search algorithm assumes that my list is ordered. Not all lists are ordered. If a list isn't ordered, about the best you can do is what's called a linear search. Alice, Bob, Carol, David, Elaine, Fred, George, Harry, Irene, John. And so I start at the beginning and I look at everything in the list, and if it's there, if it's there, if it's not, I get to the end of the list and haven't found it. Terrible performance, but it removes two assumptions. One, it removes the assumption that my data are ordered, that my list is ordered, or I have the tree structure like this. And it also removes the assumption that I can get to any element directly at any time. And we'll go through that in just a moment. Now, the book also talks very briefly about arrays. And Python doesn't really have arrays directly. Their data structures are actually built into the language, or data structures that are more powerful and flexible, though not necessarily quite as efficient. So to talk about an array in most languages is a fixed size, randomly accessible collection of data. And in some languages, such as Java, I think probably C#, it's also referred to as homogeneous, but we won't bother with that at the moment. But this, let's see if we can unpack that definition some. This is a pillbox that old people like me use. And it has, just various boxes in it. It's a collection of boxes. And this pillbox was made with 7 boxes. It could have been made with 8. It could have been made with 1. It could have been made in 2 dimensions with 7 boxes here and 4 boxes down, which would give you either 28 days or 1 week of 4 times a day or something like that. It could have been made in a lot of different ways, but Once it's made, in this case, 7 boxes, that's it. I cannot extend it to have more boxes on it. I can't shrink it to have fewer boxes on it if I decide I'm wasting space. Once it's made, it's done. And that's what we mean when we say that an array is fixed size. I can make them any size I want, but once I've made it, I can't grow it and I can't shrink it. The other thing is about random accessibility. If I only need my pain meds on Thursdays, then I can just put them in here on Thursday, and I cannot worry, not bother to use any of these other 6 days of the week. Some data structures we'll talk about would force you to start at the beginning. And if you want 2 things, you would have to do Sunday and Monday. Arrays are not like that. They are randomly accessible. If Thursday's all I need, Thursday's all I have to deal with. So that's sort of an intuitive description of how arrays work. And in most languages, which are 0 origin, and that's a nice discussion. I won't get into why that's the right decision, but this would be, Sunday would be day 0, Monday would be day 1, Tuesday day 2, Saturday day 6. And so an array of 7 elements is normally has position 0 through the length -1. So that's sort of the intuitive introduction to arrays I wanted to give. And now, in general, these data structures we've talked about, or this chapter talks about, are what I refer to as the simple machines of computer science. Just like physics has simple machines of levers and pulleys, we have simple machines, among them a stack. Now, we've all been in a cafeteria to get our mystery meat and to ignore the salad. And in the cafeteria, we see this big trolley, and it's spring-loaded, and it's got a big collection of plates on it. Well, the last plate I put on the trolley is going to be the first plate I take off. Last in, first out. That is how a stack works. And I know you're kind of looking to see something more sophisticated. These are very simple constructs. Don't look too hard. A stack is a last in, first out data store. And we talk about the top of the stack being when we put something on the stack, we push the stack down and the new thing becomes the top. When we want to get that plate off to get our veggies or whatever it is, we take the top plate off. That's the last one in, it's the first one out, and I pop off the top of the stack. Very simple data structure. Another widely used data structure is called a queue. And if we were British, this would make more sense. In America, we would probably call it a line, but somehow it became known as a queue. And it's basically waiting in a line. The first one in the line is the first one out. And when you join the queue, you go to the back of the line. So think about a ticket booth somewhere, or think about standing in line at the bank or something like that. It's a line. It's first one in, first one out, and things are serviced in order. Now, a deck is a double-ended queue. That's where the name comes from. And so in a stack, I insert things at the top and I take out from the top. In a queue, I insert things at the back and I take out things from the front. For a deck, I can insert and remove from either end. So I can insert something on the left end and remove something from the left end, or I can insert something from the right end and remove something from the left end, or something like that. So a DAC is a double-ended queue. I can insert and remove in. One thing I want you to notice about all of those data stores, you can only manipulate the edges. We can't manipulate the middle directly without pulling everything off the edge that is in our way, basically. So none of those data stores are applicable for binary search. The queue especially would be applicable for linear search, because you just keep eating into the queue until you find what you want, or the queue winds up empty, at which point you declare failure. So those are some of the simplest data structures we have. I've talked briefly about the tree structure already, and so now I would also like to talk a little bit about pointers, because they can be kind of difficult to understand. And so we're going to go back to the Brookshire machine conceptually. And in the Brookshire machine, we had what I referred to as an immediate value instruction. And so I could load an immediate value. In that case, I had an opcode, and say I want to load the value -13 into register 3. If I'm using an immediate value instruction, 2 is the opcode for load immediate. That's register 3, and I actually misspoke here. That should not be an address. That should be a value. Sorry about that. And the -13 is what gets loaded into my register. I also have what I refer to as a memory reference instruction, and there's a load version of the memory reference instruction. And in that case, the opcode is 1, my register still 3, but this third piece of information here is not the value, it's the address of the value. And so this byte here, actually, if it's 100, points to location 100, which I'm assuming has the value -13 in it. So that should be just review. We've done the Brookshire machine. If I had pointers in the Brookshire machine, and I don't, but if I did, then I might have what I might call to be an indirect instruction. I have no idea what the opcode would be, but I would have register 3 here, and I would have an address here. It would be 100, just like the 100 is up here in this memory reference. But I don't go to location 100 to get my data, -13. Instead, what I find in this memory location is a pointer, or the location of another piece of memory. And so this location 100 points me to, in this case, location 200, and that's where my -13 would be. And so this memory location 100 here would be referred to as a pointer. It doesn't directly have the data. It gives the address of another memory location where the data exists. So I think that's all I wanted to go through before our meeting on Thursday. I hope your groups are going well. And if they're not, please contact me, and I will, we can talk more about this again. Bring your questions on Thursday. So today, what we talked about are some of the really simple data structures, and talked about how they are related to the algorithms that are appropriate to work on those data structures. And the converse is true, and the data structures that are appropriate to work with certain algorithms. We've looked at binary search again and how we can view that list of things that we're doing the binary search in as a tree. And we've looked at just given very few words on stacks and queues and decks. And I've talked a little bit about recursion. Recursion is especially useful in trees. And I've talked some about pointers and what pointers are. They are places to go get information. And you sort of go hopping through memory, as it were. So I hope this helps. Send me your questions, bring them to the meeting on Thursday. So hope this helps. See y'all later. Bye.